This is part 3, GCBASIC support investigation for this floats issue, singles. Okay, so we're going to show you some tricks, not tricks. These have been published, but we need to prepare to go deeper into this issue. So what I'm going to do is I'm going to show you MPLAB is MPLAB, and I've created a project in here, and I'll show you how to do all that in a bit. But essentially what we're going to do is we're going to take some source from GCBASIC, and we are going to compile it in here. So this is the project I created, and I'll show you how to do this in a minute. But basically, this is no, I'm just using something called First Start, okay, because that's the one that I happen to pick. And that in there is the source program for what I'm actually dealing with. This is the same program. I have added into the latest compiler a little date stamp in here, a subtitle date stamp. I'll explain what we're looking at shortly, but this is the program that we've been dealing with. And if we cursor down in here, I have got comments turned on. Okay, so here it is, UPC5, 3 to 9 I've got at the moment. Legacy method, oh, if you want to know what that is, I'll tell you. And then this is the actual loop, and here's the next statement. So what we can do inside of MPLAB is we can actually compile this. I'm going to just shuffle things around on the screen here so we can see it all happening. Is that I'm going to get it on the screen? Yeah, look, I've got a very small MPLAB here, okay, but we can sort of see it because you can get to see what happens. So I can then production, build that main project, and it's building the source from GCBASIC. Now what I can do, I can then come into here and I can, oh, it's still doing it. I can build for debugging, which I just clicked. 2 seconds. Now I can walk the code. Discrete debugger is just finishing off its operations. I'm just out of shot from yours on the screen. It's not quite finished yet. It's loading the libraries, the linkers, sorry, loading the system in the background. There we go. So it's done it. Debug, discrete, launch, debugger main project. And it takes us into the GCBASIC generated source code. Now it's sitting at BAS program start, and this is exactly what we need to see. Now, we have seen before that we can disassemble the numbers that are going into GCBASIC into that calculator. Remember the calculator in the previous videos? This calculator here, we're going to be using that and other tools to walk the code. So this is a piece of failure code. The last run I had on this, I've got this. It's stuck on 3, and I can see I'm getting corruption on the incoming number. Trying to figure out what that is. So if we remember how GCBASIC works, it essentially it does a jump to vector 0, and then once from vector 0 it goes off to the program start. So I press function key F7, and look, it's done that for us. Let's get rid of this window. Don't need that at the moment. And then it goes to initsys and then USArt. We know the problems aren't in there. So what we can actually do, we can actually put the cursor on the next line down here and press function key F4. And if I've done it correctly, which I don't think I have, oh, there you go. It ran to that line. So it runs to the line. So I can press function key F7, and it will now walk the it will walk the code. And I want it to walk the code down to the initialization of UPC here. But what I'm going to do, I'm going to put it exactly here. I'll explain why. Run to there. Why is it only doing one step? Run to cursor? Maybe I'm not putting the cursor on it properly. Run to cursor. I'm doing it. Run to cursor. Finally, it's got there. Okay, so this is actually going to show you how it loads UPC into that variable. Okay, now the compiler the executable that's run, has analyzed the constant 5.00 and it's going to put it into the UPC memory. And that's a 32-bit number, 4 8-bit. So we're going to see 4 bytes being updated. And the first one is going to be set to 0. You can see here, F7. The next one is going to be set to 0, which is in here. Then the next one is 160. The next one is 64. And then put it in a variable called UPC, UPC high, UPC U, and UPC E. And that is the number. Now you might go, well, how's that all work? Well, watch this. I'll put it in the calculator down here. Look. Here's the calculator. This is the low byte. This is the H byte. What was that number? 160. 160. What's the next number? 64. There you go. 64. Convert. And it says that that number is equal to 5. So now we have a method of walking backwards and forwards. And that's what this calculator was built for. Because you can't do this. You have to convert between IEEE numbers, microchip double numbers, single numbers, and these representations at high speed. You couldn't do this any other way. There is no other calculator that does this. So I'm going to move that down. So we now know that the compiler, the executable, has set UPC to 5. We know that because we've proven it. This puts something on the screen. Look, not interested in any of this. Okay, so I'm going to set a break here. Look, toggle line break, Control F8, and it runs down to that line. So it now says I'm inside of the for next loop. Well, the for next loop, it takes the variables and it puts them into UPC. We've already set UPC. I did that as a little test to make sure we knew what we were doing earlier on. So now we're going to put the first value, which in my case happens to be 3. 3? Why would that be the case? Well, that's because it happens to be the number. So if I come into my calculator and I can see in here, it's going to go 0, 0, 0, and put 64 inside of here. So let's just check that that is actually number 3. Oh, it's number 2. Oh, of course it'll be number 2. It's 1 less than the start value. It will become obvious in a minute. Yeah, that's correct. It's 2. It set it to 2. UPC will be set to 2. Let me walk that code, F7. So now UPC is set to 7. How do we know that? Well, over here in the variables, I've got UPC, look, and it's sitting at address 78, look. You go, oh, this is so complicated. No, it's not, because if I come up to the top of the source, look, and I find the variable called UPC, and I'll go up previous. UPC sits at address, I expected to see 78. Oh, it is 78 now. UPC 78, that's the lower byte. The next byte is 79, the H byte. Then the A is the next byte, 7B. So we can look at RAM. We can actually look in the RAM of the chip and go, ooh, what's going on? File registers, find hexadecimal 78. 78 is here, and it's set to 0, 0, 0, 4, which we now know is equal to 2. By the way, this is how you debug. Now, what the for next loop is going to do, it's going to increment that UPC value that's set to 2 initially, and then later on it will loop back to that and increment it again. That's how it works. It initializes it 1 less, then it increments it the first and says, is that greater than, or is it less than or greater to? And we'll see it do that in a moment. Right. So what it's now doing is loading UPC into a temporary variable because it's going to do a compare. So there's a variable called sys single temp A, and it's just copied that across. It's therefore system single temp A should be the same value as UPC, and then it's going to test that against the target variable, which is, as you can see, 0, 0, 128, 63. Let's not struggle. 0, 0, 128, 63 from memory, correct, convert 1. So Evan was wrong. What it's going to do, it's going to add 1. It's going to add 1 to add the increment value of the step to UPC by using this systemp here. Okay, so it's going to go off, it's going to load in UPC, which is done. It's going to add 1 into sys single temp B, and then it's going to call the function sys add single sub x. There you go, single sub single here, and when it returns, the x value should be UPC plus 1. So if I put a break here, Control F8, and run it, when it returns back, UPC should be equal to 3, because UPC is currently. So let's have a look at that. Let's have a look at that in a moment. I'm just back in the calculator to make sure that my assumptions are correct. 40, oh, it's 40 hex. What's 40 hex? 64. Yeah, it's currently to 2, so I'm expecting this to come to a value of 3. Let me press function key F5 to run it. Better be in the calculator when I do that. 5. It's done it, so it's come back, and it's come back with a 0. Oh, 78 is here. 0, 0, 4. What's that number? It's 40 hex 64. Oh, it's come back as 3. So that tells us that it added 1. So the function that is called sys add single added 1 to it, which is quite correct. I'm pretty confident, by the way, that that routine's working properly. I mean, that is highly complex. I mean, so recap: A and B, result comes back in C. X, sorry. A and B, result comes back in X. Always the same, right across the whole of GCBASIC. Okay. And other compilers do the same trick, but it's not hard. So it's now going to load. It's loaded UPC back with its incremental value, which is 004040 hex, which is equivalent to 006464 decimal. I wish that this calculator had a hexadecimal convert in it. I'll speak to him tomorrow to see if he can do that for us. It's equal to 3. So now we know that that part's correct. What's he going to do next? Well, it says here, single string, pass it UPC. I'm sorry, but at this point, this looks all correct. So it's going to put UPC into single num, high, upper, and the E. So these are the 4 bytes. And then it's going to call the function I think that's broken here. Could be somewhere else, but probably inside of here. UPC single. Well, let's find out if that gets UPC move. Let's have a look. F7, F7, F7. I'll sit on the R call. I want to look at this variable called this variable here. I am just going to go into my GCBASIC source, Control F, and that's sitting at address 1711 hex. Okay. So in here, we should see 00400. We should see this value at starting at address 11. address 11, 0, 0. Yeah, that's correct. So when it called the single to sys string, when it called it, it was correct. So the incoming value is correct. I'm going to let that run, and what this does, it goes in and then puts it on the screen. Okay, comport one, whatever. All right, I'm going to let the whole of that thing run to see if it corrupts our variable. First test, because if it's corrupting it inside of that function called the string handler, the single to string, then if our variable comes back as broken, and our variable broken will be the one that's at 7.8, this one here at 7.8, that would tell me the problem's inside that function. So I'm going to run it to here, function key F8. Oh, did that run? Function key F8. Function key F5 to run it. It's run. Okay, so it's returned back. 7.8 is correct. Look. 7, that is absolutely spot on. So our variable is equal to 3, remember? Because that's 0, 0, 64, 64. That's 60, and at 11, address 11, this has not been corrupted either. Now, it puts it on the screen with a comport stuff lot, and then there's a next statement. And this next statement is essentially, it's going to put UPC into the A variable. It's going to compare it to something that's 0, 0, 16, 65. 0, 0, 16. By the way, we have to, this is how we wrote it in debugged it in February. It's going to go to 9. So it's going to say, is UPC less than, here it is, look. It's going to call this function here called compare less than single. Compare than is it less than? Okay. And it's saying, is it less than 9? It is essentially less than or equal to. So we know that that value is going to work because it's already returned back. So we can run it. We can run it to here, Control F8, or we should run it to there really, Control F8. We'll put a break. It's just done it, it's come back. Let's have a look at our variable, 78. It is spot on, has not been corrupted. So if I press function key F7, it's now going to loop back to the beginning of the for next statement. It's going to put UPC into the A variable. It's going to load the 1 into the next variable, and then it's going to come back and do it. So I'm going to run it, and we're going to see what the result is. The result has changed to 00840. Guess what I'm going to do? 00, what was it? 008, that's 120, that's 128, isn't it? 64, convert, equal to 4. So we've proven that the adding is correct. But I think I knew that because single string 3DP worked. Tick. How do you make this all work? Okay, first of all, you need to install MPLAB 6.2. If you install MPLAB 6.2, I will delete this project, and then we'll just say that I'd like you to sort of get this up and running. So I'll delete this project here, and we'll just recreate it all. Projects, delete. It's pretty simple to do all this. Delete that source. Great. So MPLAB, just pretend you've opened up in a minute. We'll do it properly. So let's go into GCBASIC. That is GCBASIC in here. Here's my source code as it was. Function key. The first thing is install MPLAB 6.20. Job done. Function key F4, preferences. In the compiler tab, select in the drop down, pick AS, click tool variables. Just check because I don't know what version you're on, right? That this address here, which is the MPLAB-X directory, is set to 6.2, which is the latest version that's installed. Okay, all right, and check that this is correct. This is the pick AS location. This is a compiler. Okay, version 2.50. Those are the two versions you should find if you install MPLAB 6.20. Should work. Press OK. That then changes the compiler from the internal compiler of GCBASIC to PKS. Good. If you now compile a program by pressing function F6, down the bottom, which you can't see, I shall just cursor up. It's changed it. It says here, look, assembling using PKS, and it's assembled the file. And what it's done, it's generated what's called a .s file, and that .s file is what we need. It's like an assembly ASM file, but it's a .s. So if you wanted to see that, press function key F4 in GC code and type in the word open, and it says open S. It opens up a file that looks just like an ASM file, but it's not. It's formatted for the different PKS compiler. But it's essentially the same. I just did a load of conversion. I wrote a converter between the two. And here it is. Look, this is the program we were looking at previously inside of MPLAB-X. So MPLAB-X, new project, application project, next. 14K22, pick it, simulator, next, select PKX 2.50, doesn't matter which version you pick, I don't really care, 14K22 is the name, job done. We've created a project, then we can debug it, do some loading stuff. If you look at this PKS file back here, just to copy the path, to make it a bit easier for yourself, you can now add that into your source files here. Add an existing item. Type in that sample you just cut and pasted. Sorry. Select production just to make sure it all works for you. Build the project. We're compiling up inside of GCBASIC. Debug. Takes a few minutes to load in the stuff. Good, it's done it. Debug, discrete bugger, build for debugging. Build successful. At the bottom, it loads in the assembly. It loads in the other stuff. All the symbols will be loaded because it takes the symbols out of the GCBASIC source, which you can just about make out on the left-hand side there. I'll just throw that across. Look. Good. Discrete launch the project, and now if I double-click this bit of code here, we're back where we were. That simple. F7. You can now walk the program in the debugger. Now, if you have a PickKit4, you can actually walk the code with the chip. Now I got PickKit4, so we will eventually be in there. Now, I honestly believe that the issue is somewhere within the routine single to string. Sorry about my pausing. I'm trying to keep thinking what I'm saying here. So I think it's actually inside of this routine here. I think we have the proof now to go back to Clint and say to Clint, he wrote it. We have an issue here somewhere, but I'd like to isolate it for him because he can fix it once we've done all the heavy lifting. Be a bit unfair to throw him in at the deep end. I think it's somewhere in that routine. That's the wrong one. in here. But we know from this piece of work we've done here that if we run that, it's in there. So remember where we were? File registers. 78 is where our address was, but we have to go, 0040. We know that's number. We know that's a number. I can't remember. 64 is 3. So we'd expect to see 3 appear somewhere in these routines. So now, if you walk inside of here, you start to see the complexity of this routine is extremely complicated. This is a credit to what he did, but there's clearly a bug somewhere in here. And essentially what he has to do, I put some clears in there yesterday. That might not be in your routines because I wanted to see if I cleared everything out, it actually helped. Your routine won't do the same because I added in a load of clears to try and isolate the issue. So first thing he does, he didn't actually clear everything down, but that wasn't the problem. So I just went through yesterday and added in all these variables and put them set to 0. It seemed like a logical thing to do. And then the first thing he does, he loads in half of the variable he loads our variable, which is a variable. He loads that into memory and then analyzes it, breaks it into the mantissa part, then calculates what the mantissa value is, and then the integer value, and then scrunches it together with a load of text and then puts it on the screen. It's very accurate. However, it's very, very complex. So I think what I'd like you to do is try to get to this stage, which is install MPLAB. Make sure that you can compile .s file because that's where we're heading next.